Go, Roger Rabbit. Hello, everybody. Hi. Welcome to another exciting adventure in Antirelativity. Hi. Welcome to another exciting adventure. I'll just turn that other sound off, sort of. What's that? I'll just turn that other. Right. Okay. So I'm here somehow or other. Let's go to my slides, hopefully. Thank you, Franklin, for opening the session. Let's see. Slides. Oh. Share screen. Oh. Doesn't show it. Oh. Cancel that. Present. Oh, slides. That's this one. No, it's not working properly. Oh. Let's see. Got slides there.
If it isn't working, can you just email me your slides?
Share screen. Share screen. Oh. I'll catch that one. So that's okay. Share. Okay. Let's see, can anybody see that, or is it just me?
No, we cannot see that. So all I'm seeing is a blank white screen for your share screen.
I think it's just me can see this. Hold on a moment.
Just like we had the problem with the video. So Roger, I think maybe we should play the video, and you need to send me by email your slides.
I don't seem to get the slides then.
But shall we go ahead and play the video instead?
Can you hear me, Franklin?
Why don't you go ahead and just give an introduction to the video, and then we'll work on the slides later.
Right. Go back. No sound.
Now, this is a 20-minute video, Roger. Did you want to play all of it or just some of it? Now, people are saying that there's no sound from Roger now, although
Franklin, you there?
I mean, do you guys hear my sound?
Hello, Franklin. Are you there?
I'm here.
Seem to have lost Franklin now.
People are seeing this. People are saying that we have a sound problem. People are saying they can't hear you. Okay, they're saying that it was they turned down their speaker, but okay.
So still having problems.
Hopefully
Franklin would come back.
Well, Roger, I'm here the whole time. Do you hear me?
Hey.
Do you hear me, Roger?
Franklin.
Do you hear me, Roger? So, Roger, you need to send me by email your slides so I can.
Yeah, okay.
And in the meanwhile, shall we play the video?
Yeah, play the video.
Play the video. Did you want to play all of it?
Yeah, play all of it. Yeah, okay.
Okay, so send me your slides. We'll get that ready. Okay. And why don't you do an introduction to the video?
Okay. So, introduction to the video. Sorry for all the problems. Thanks for handling. It's about loophole in special relativity. The problem with special relativity is that it's a bit ambiguous, and so it can be interpreted in different ways. And so when it's talking about light speed being constant, what exactly is that supposed to mean? And so the video is going to try to deal with that. Thank you.
All right, let's go on with the video here.
Okay.
Okay, let's do this and do that.
It's often said that the theory of relativity proves to us that time and space are relative. Indeed, this appears to be an inevitable consequence of Einstein's famous speed of light postulate, which states that inertial observers must always measure the speed of light to be constant, no matter what their own speed is.
Also, Roger, you can...
Alas, there's a world of hidden meaning in the word measure, which, when scrutinized sufficiently, gives rise to a particular disconcerting loophole to the theory. And should we choose to exploit this loophole, it can allow us to do what's been considered unthinkable blasphemy for the past century. Restore absolute space and time to modern physics. This is Dialect with The Loophole in Relativity.
The speed of light is constant, and it always shows the same value for all frames of reference.
One of the most fundamental physics facts is that the speed of light in a vacuum is constant for all observers.
The speed of light is measured to be exactly the same by everyone, no matter what.
Astonishment. Physicists discovered that this precise speed is absolute. Any object moving at 299,792,458 meters per second will have this exact speed in all reference frames. It is called the speed of light.
It's the inviolable law of modern physics. Each and every observer must measure the speed of light as constant relative to their own frame of reference. But what if this wasn't a law at all? What if, truthfully, it was just a narrative? Okay, come on, what do you mean, narrative? As all those videos clearly stated, that observers measure the speed of light to be constant in any inertial frame is a well-known, well-proven, well-demonstrated scientific fact. Well, yeah, except that it's not. You see, there's actually a bit of a hidden caveat to the speed of light postulate most people don't know about. And what it tells us is that it's not the speed of light which is measured to be constant for all observers, but rather the two-way speed of light which is measured to be constant. What's a two-way speed? Well, it's where you take something like a beam of light, fire it, reflect it off something, and when it returns to you, make a judgment about its average speed based on the round-trip distance traveled and the total trip duration. In contradistinction, a one-way speed would be firing a light beam in only one direction and measuring the time it takes to cross a given distance. Now comes an incredible fact. No one has ever measured the one-way speed of light before. All our measurements of the speed of light are two-way. Now, Veritasium already covered this topic in a very excellent video a few years back, which we'd highly recommend you watch. But the gist of it is that every empirical experiment which has ever been performed in order to measure the speed of light has always utilized a two-way measurement, because it's actually impossible to carry out any sort of one-way measurement. Thus, when we say things like that the speed of light is constant relative to all observers, this is actually unfactual, as it neglects the reality that there's an entire subset of one-way measurements we've never been able to make. Now, before you object and begin writing something in the comments section about how we must know the one-way speed of light to be constant because of this or that, please take a minute and scroll through the 100,000 plus comments on Veritasium's video, as you're likely to find your idea or objection already addressed there. Now, Veritasium does a relatively good job at going through different types of experiments you might try to set up and demonstrating why in particular they'd fail. But he only vaguely dances around the fundamental reason for why it is that we have never measured the one-way speed of light. Essentially, that reason is because we don't have anything to measure the speed of light relative to. To measure the one-way speed of light would require utilizing a signal much faster than that of light, which we obviously don't have access to. In the absence of a faster signal, measuring the one-way speed of light across a given distance requires first synchronizing two spatially separated clocks. But two clocks can only be synchronized by first passing information between them in the form of light signals. See where the problem lies? To measure any one-way speed, we must first adopt a synchronization convention. But this in turn requires making an assumption about how light travels from one clock to the next. Einstein understood this very clearly, because adopting a synchronization convention constitutes the first and foremost part of his famous 1905 paper. Here, he acknowledges that our empirical conception of the speed of light is in fact a two-way one. Then, to resolve this issue, he makes the most crucial assumption of his career. In referring to two clocks, A and B, which are in the process of being synchronized, he writes, "We have not defined a common time for A and B, for the latter cannot be defined at all unless we establish, by definition, that the time required by light to travel from A to B equals the time it requires to travel from B to A." This assumption yields the resultant Einstein synchronization condition. Okay, halt the presses. So Einstein assumes that light must travel between two clocks in a completely symmetrical fashion, no matter what the speed of the observer is. And then he defines time for each and every observer through this assumption. Well, if the one-way behavior of light is symmetric, or more formally isotropic, for you, then for light to still have a constant speed everywhere means the one-way behavior of light must be asymmetric or anisotropic for observers in motion with respect to you. But because they also assume isotropic light behavior in their own frame, they'll synchronize their clocks differently than yours. Thus, plainly we can see that the relativity of time and space is a direct consequence of this assumption about the one-way behavior of light. But therein lies the problem, because this assumption is completely arbitrary. If the one-way speed of light is not empirically observable, this means it's equally probable that in synchronizing your clocks A and B, the light signal you sent out from clock A traveled at a slower than speed of light velocity towards clock B, then zipped real quick back towards clock A at a faster than speed of light velocity, or vice versa, such that the total average speed was that of the speed of light. If this happened to be the case, then the notion of length, time, and simultaneity you constructed in your frame using Einstein's assumption would in fact be a false one. Indeed, it didn't take long after 1905 before others picked up on this arbitrariness in Einstein's assumption. Most notable to do so was the philosopher Hans Reichenbach, who in his work The Philosophy of Space and Time described the notion of simultaneity as being regulated by a sort of uncertainty principle. "Simultaneity is not a matter of knowledge," he wrote. but of a coordinative definition, since knowledge of simultaneity is impossible in principle. Reichenbach asks us to consider 3 times, t1, t2, and t3, corresponding to the respective times that a light signal is sent out from clock A, that it reaches clock B, and then returns again to clock A. Simultaneity can then be defined via the following relationship. T2 equals T1 plus epsilon times T3 minus T1, where epsilon represents the uncertainty in the one-way speed of light and can range from anywhere between 0 and 1. As Reichenbach points out, the Einstein convention chooses a value of 1/2 for epsilon. This means we assume the light beam in our frame spends half the total time traveling from clock A to clock B, and half the total time traveling back. If we instead choose a value of 2/3 for epsilon, this would mean we assume the light beam in our frame spends 2/3 the total trip time traveling from clock A to clock B, and 1/3 the total trip time traveling back. As Reichenbach clarifies, we are free to choose whichever value of epsilon between 0 and 1 that we like. Just like deciding where the origin of a coordinate system should be, it's a completely arbitrary choice. Einstein's convention, Reichenbach notes, does achieve greatest mathematical simplicity, as choosing a value like 2/3 for epsilon would lead to quite the headache mathematically for observers. But Reichenbach makes it clear the choice of 1/2 for epsilon is not an empirical necessity, but rather a mathematical stipulation. He then goes on to note that determining absolute simultaneity would require a faster-than-light signal. So unfortunately, observers are stuck with choosing some value of epsilon, whatever it may be. From this he implies that space and time must still ultimately be relative, even if it's not quite the mathematically simplified version of relativity Einstein presented. But here Reichenbach neglects one incredible, crucial point. He, along with Einstein, implicitly assumes all observers must choose the same value of epsilon. But nothing restricts different observers from choosing different values for epsilon. This is our loophole. Because different observers could always choose different values for epsilon, such that their notions of simultaneity wind up being the same. That is, given any collection of observers A, B, C, etc., whose velocities with respect to some given frame are v1, v2, v3, etc., we can always find a corresponding set of epsilon values, epsilon 1, epsilon 2, epsilon 3, etc., such that each and every observer constructs the same notion of simultaneity, and therefore the same notion of space and time. And thus at once we've done the impossible, restored Newton's notion of absolute space and time to relativity. This is easiest to grasp with a space-time diagram. First, take a given observer who considers themselves to be at rest and is synchronizing their clocks with light signals. As they move through time, their space-time diagram will look like this. If they adopt Einstein's epsilon 1/2 convention, they will draw their line of simultaneity directly down the middle like this. Next, consider an observer in motion relative to this first observer, who is also synchronizing their clocks using light signals. If this second observer also uses the 1/2 epsilon convention, then they will draw their line of simultaneity such that it will appear slanted relative to the first observer. Because these planes of simultaneity are slanted with respect to one another, time and space will then be said to be relative for the two observers. But now we can recognize that there's no real reason the second observer has to adopt the epsilon 1/2 convention. They could instead adopt a different value, such that their plane of simultaneity would align with the first observers. Then, between these two observers, there will be total agreement on all notions of time and space. Physically, this amounts to choosing a particular master frame, and having all observers agree that the clock ticking in this frame represents true universal time. But of course, in special relativity, choosing such a privileged frame is disallowed, since the principle of relativity requires that the laws of physics take the same invariant form in every inertial frame of reference. But again, we can see the circularity here. The laws of physics are expressed via space and time, so for them to indeed take the same form in all inertial frames of reference requires all inertial observers to build their notions of simultaneity according to the exact same recipe. Meaning observers would all have to choose the exact same epsilon value. Meaning it would have to be factually true that the one-way speed of light was the same for every inertial observer everywhere, in order for it to be factually true that the laws of physics have the same form in every inertial frame. But again, the one-way constancy of light is not a fact. We thus assume one-way light behavior to be isotropic, thereby contriving space and time to be relative, in order to give the laws of physics the appearance of having the same form for all inertial observers, because that's the mathematically beautiful description we prefer. This, of course, is the very definition of a narrative. Indeed, it wasn't until 1976, over 70 years after Einstein published his theory, that anyone would appear to hit upon the idea of different observers assuming different values for the one-way speed of light. Such a method was finally considered by these physicists in a paper entitled A Test Theory of Special Relativity, Simultaneity and Clock Synchronization. The conclusion they drew? A theory maintaining the concept of absolute simultaneity can be obtained in this way, which is empirically equivalent to special relativity. Okay, let's pause to summarize everything so far. Firstly, we've learned that the central assumption from which special relativity stems, i.e. that the one-way behavior of light is isotropic in all inertial frames, is empirically unverifiable. Secondly, we realize this implies observers are free to assume whatever one-way behavior of light that they like in their own frames, a choice represented by Reichenbach's epsilon value. Thirdly, for multiple observers, we know we can always select a particular set of epsilon values such that everyone's notion of simultaneity exactly aligns. Lastly, we note this doesn't change the laws of physics. It just changes how we express them. Naturally, then, we should be led to ask, what exactly do we stand to gain in adopting the notion of absolute simultaneity? We can answer this by considering the physical meaning of anisotropic light behavior. If we send out a light wave in every direction, since the two-way speed of light is still factually a constant, then if light moves more slowly in one direction, it must compensate by moving more quickly in the opposite direction. Thus, for any spherically shined ball of light, if the one-way speed of light were anisotropic in your frame, the center of the sphere of light would move steadily away from you, like this. Values of epsilon further and further away from 1/2 would correspond to the sphere moving away from you at a faster and faster rate. Thus, it would be as if the light sphere were expanding at a constant speed in some particular frame, and you were in motion relative to that frame. Now, if you've seen one of our recent videos, what time dilation actually is, the puzzle pieces should be seriously starting to fall into place for you right now. Things come together even more when we make note of our prior observation, that if you attempted to synchronize your clocks in a frame where you assume the one-way behavior of light to be isotropic, when in fact that behavior was anisotropic, the notion of space and time you constructed would be a false one, a sort of projective map. Indeed, by conjoining this so-dubbed epsilon choice interpretation with that of dynamical relativity, we will be able to do what was supposed to have been impossible. Give a fully physical, fully mechanistic description to the theory of relativity. Yes, that means that everything from time dilation to length contraction to the symmetry of these things between observers and motion, all of this can be exposed as the consequence of simple, physically causal phenomena. Stick around with our channel and you'll find out exactly how. Now, finally, a big thank you to our Patreon supporters for continuing to make all this possible. Knowing how many people out there are looking for real answers has kept us motivated, kept us going. So until soon, this has been Dialect. Thanks for watching.
Yeah, that's the end of that video. Thank you.
Okay, so Roger,
Okay.
I've got your slides here.
Yeah.
So let's put up your slides and see whether we can get that to work.
Okay, thank you.
Okay, just a moment here.
Yeah.
I need to start your slideshow. Slideshow. Play from the start.
Funny games. Okay.
Let's see whether I can share that. Present. Share screen. Let's see here. And when I play the slides, it kind of hides all of my controls and everything.
What, you having problems?
So let me see here.
Okay.
Let's see here. Window, intro screen. Let's do that. Okay. There we go. I think we've got that on. So I'll let you go.
Hey, excellent. Thank you. So this should have been the other way round. Should have presented the slides first and then done the video. So things might get a bit confusing because of the way it's been going around, the way it's been going to now be switched around. Okay, next slide, please, Franklin. Next slide. Is there? No. Okay. Well, if you're there, Franklin, can... Oh, great. So the question is, does lunar ranging experiment disprove special relativity? And as you go through the details, it's going to get confusing, and it's going to be particularly confusing if you were coming at it from the other way around now, that we're seeing the video first before these slides. And the answer to the question is it's arguable. Those pro-Einstein relativity versus those anti-Einstein relativity, well, it just ends up in big arguments. And in my view, those people who are pro-Einstein's relativity are not playing fair. So next slide, please, Franklin. If we can get to the next slide. I'm still seeing slide 2 at the moment. Okay, slide 3. So first of all, I need to clarify things from previously. In Antirelativity 4, I pointed out Einstein's relativity keeps changing. And the importance of that is when we dealt with the Sanak experiment in Antirelativity number 2, that should have ideally disproved special relativity. But unfortunately, special relativity gets modified, strokes changed by those defending it. So the changing of relativity extends to changing what is meant by the postulates, etc. So next slide, please, Franklin. And so I'm seeing slide 4 now, and it says in 1920, Einstein was saying there was an ether, but that is of course arguable, and the link I've provided there. And then Einstein in 1955 revises his book, The Meaning of Relativity, and he dies that same year. So that amounts probably to his last thoughts on relativity. And there is no mention of ether in that book. So what does that mean? He seems to be saying in 1920 there's an ether, and in 1955 he doesn't seem to mention it anymore. So the options are, in 1955 he has abandoned what we were saying about ether in 1920. Or another option is in 1955 he expects what he was saying about ether in 1920 to still be accepted. So, and a third option is he means something else. So this is the problem with Einstein. You try to understand what he's doing, and he's not telling you in sufficient detail of what he's doing. One minute he's saying one thing, and later he doesn't seem to take up on that issue, and maybe he's abandoned an idea which he was talking about earlier, or whatever. So he's just Einstein is just a mess, really, in trying to understand what relativity is. And there's another book on relativity. It's by Pauly, and it seems to be a very good book on relativity. It's written by Pauly, who's, I think, friends with Einstein, so he sorted out what relativity is supposed to mean. But Einstein was disagreeing with what was being said about relativity in that book. So next slide, please. So here we go. In the theory of relativity by Pauly, it says, I consider the theory of relativity to be an example showing how a fundamental scientific discovery, sometimes even against the resistance of its creator, gives birth to further fruitful developments following its own autonomous course. And of course, by the creator of relativity, he presumably means Einstein. And he's saying that the person who's created relativity, Einstein, is not necessarily agreeing with how the theory has been developed. And what's happening there with Pauly, he's appealing to the theory itself as the higher authority over what Einstein says. And what Einstein thought about it is probably summed up by his quote from him, which he says, since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore. So Einstein is resisting the changes which he calls mathematicians are making to relativity. And that's the situation we have with it. Everything's just changing in relativity, and Einstein's not necessarily agreeing with it. And Einstein gave a series of papers on relativity and kept changing his mind. And we have continual reinterpretation of what Einstein meant. And that's slide 7. So on the next slide, 8, thanks. So there was an early attack on Einstein. He became famous in 1919, and about one of the first people who was attacking relativity was this experimental physicist who was German. And the trouble with that is that in the time when people started attacking relativity, 1919 onwards, it got all involved with anti-Semitism, and people, it was the rise of the Nazis, and they hated Jews, and Einstein was a Jew. And so what these people were saying was being dismissed as they were just being anti-Semitic. But you have this person who seems to be criticizing Einstein from the physics side of things. So next slide, please, slide 9. So this is the one of the papers which deals with early criticism of Einstein's relativity. Next slide, please, slide 10. So what we have is in slide 10 saying that the physicist Girk was noting that when he's dealing with Einstein's relativity, it seems to be a moving target, by what she means that Einstein's relativity keeps getting amended, stroke changed. So Girk was criticizing Einstein's relativity, and he was finding that what was being said about Einstein's relativity was changing. So this is an interesting, in slide 11, we have an interesting article in the American Journal of Physics. It's called Two Myths of Relativity by this person, Rolf. And he notes that there's misconceptions about special relativity are common and pernicious. And in that paper, he's addressing two of those myths. And what he notes in that paper, one of the things he notes is that the meaning of constancy as speed of light has changed its meaning from what Einstein was talking about in 1905. So what it is another example of Einstein's relativity keep changing. Next slide, please. 12. So going by Einstein's first paper, putting aside the translation problems I think are involved in that, and Einstein gives the following equation quoted there. Next slide, please. Slide 13. So, yes. So what happens is you have c as the speed of light, and it can be reinterpreted as meaning the two-way speed of light. And so you've got speed of light going in one direction as being the one-way speed of light. It goes from a distance, hits a mirror and gets reflected back to a clock, and you recorded the time that light has gone forward and back from that mirror, and that is the two-way speed of light. But in the one-way direction, that is not being measured. So it's a changing interpretation of what Einstein was saying, to say that he was talking about the two-way speed of light being constant. And in the context of that, the one-way speed of light then could be variable. So when people start the lunar ranging experiments, when they say they show one-way speed of light variable, that could be the old understanding of special relativity, and special relativity might really be interpreted as the one-way speed of light is variable. It's only the two-way speed of light being variable. Next slide, please. This is the sort of papers that are out there. This is shown on slide 15. Next slide, please. And it explains the details. Next slide, please. And this is another paper saying about the data they're collecting from the Lunar laser ranging project contradicts Einstein's relativity. Next slide, please. And this is the abstract on it. Next slide, please. So when he talks about MME, that means the Michelson-Morley experiment. So what you're doing is reinterpreting the Michelson-Morley experiment as well. Next slide, please. This is another paper which is claiming that special relativity is wrong from the lunar laser ranging experiments. What you're doing is you have a light being measured between the Earth and the Moon, and the speed which these papers are, the light speed these papers are claiming is not constant. Next slide, please. And that's the conclusion of that paper. And next slide, please. So, and that is an example of somebody disagreeing with the previous paper. So these papers are saying light speed in the lunar ranging experiments, which the papers which are saying that it shows light speed is not constant, then you've got other people coming along and disputing that as well. Next slide, please. Ideally, need to go into more details about that, but part of the problem is the revision that seems to be going on with the light speed constancy, and that's when I was going to get to this video, which you've now already seen. So this whole issue is really complicated because like Einstein's relativity is not a precisely defined theory. It's something which is a moving target. It keeps changing. So when you get papers saying, oh, such as the lunar ranging experiment, oh, it disproves relativity, well, somebody's going to come along and disagree with you because they're interpreting relativity a different way. And so that's pretty much my summary at the end. Thank you. That's the end of the slides. Thank you for attending. So we can now open it up to discussion. What does everybody think? Yeah. Results of experiments get disputed and Einstein's relativity keeps changing.
So you're muted there, Dennis.
Okay.
You gotta unmute yourself.
Hi, Dennis.
Dennis, you gotta unmute yourself.
Yeah. Thank you for attending. Okay. Yes.
Sorry about that. And James P. Wesley's Scientific Physics, Chapter 1, it's about 50 pages. It describes a number of experiments that are one-way experiments. For example, starts out with Romer, an astronomer of a long time, whose results were known to Newton, and it seems to be heavily influenced Newton. And he would view Saturn or Jupiter, I can't remember which one, and one of its moons was Titan, which is a big moon, a really big one. And he noted that if you accept the usual equations for orbital motion about the sun, you could measure the speed of light in one direction because you could get the precise time that this Titan was eclipsed by the Jupiter or Saturn. And then you could track this as it went around, as the Earth went around the sun. And you could then calculate how much time differential occurred between since it's known that if you accept the orbital motions of Newton's law of gravitation, you can then compute when the Titan should be eclipsed by the mother planet, and the difference in when you're in different parts of the Earth's orbit. So it's an algebra problem to calculate roughly the speed of light in the one-way speed of light, if you assume that the sun drags the ether around throughout the solar system, at least around Jupiter and Saturn. So that was, and then Bradley went on later on after Newton to extend Romer's ideas. And then it ends up by giving two experiments performed by Monstein, Christian Monstein, who worked closely with, he's a Swiss radio astronomer, now retired, worked closely with Wesley. And he has two experiments, one a chopped light experiment and another coupled mirror experiment, both which measure fairly accurately velocity of light in different directions. And all these numbers...
Sorry, you seem to be losing Dennis there, but if I can butt in and say that, hello, sorry, Paul, you lost you there for a moment. Are you back again now? So if I can butt in now, what you're talking about, the Rommel experiment and so forth, that was done in the context of Newtonian physics. And the assumption then
Newton's
was
law of gravitation. It was Newton's law of gravitation.
Yeah, but
NASA in its probe around the solar system used Newton's laws and was off by an extremely tiny amount.
Yeah, sorry, I'm butting again. The trouble is with relativity, it goes off in too many different directions. And this talk was not really dealing with Rommel, and it wasn't dealing with Bradley. But in the context of when that was brought up, those things, Rommel and Bradley, the theory at the time was Newtonian physics. And those experiments would have been interpreted from a belief in absolute time and absolute space. So that's what those experiments were being interpreted from. And now Einstein's come along and he's presented us with this idea that time is relative. And so you've got a problem with clocks. If you've got clocks, you've got problems of trying to get the clocks to synchronize. So the interpretation of those experiments is now different. It's different.
Well,
in Einstein's context, they are different. You've got a problem now with measuring light speed in one direction, which is a one-way light speed. And so when he set up his paper, what it gets interpreted now, what he was dealing with was two-way light speed as being constant. He was not dealing with one-way light speed being constant. But that's the interpretation now being imposed on Einstein. So Einstein has created all this confusion. And if you bring in Rommel and Bradley, that they are now supposed to be interpreted by what Einstein is saying and not be interpreted by what Newton's saying.
Ian Collin has a paper, several papers actually published in Geology and Electrodynamics, where he shows that according to his theory of electromagnetism and radiation, the light speed is not constant, and he even proposed an experiment where his theory could be tested.
Yeah, but sort of like it's still the problem that Einstein in his paper 1905 is talking about light speed being constant. And so does that mean the one-way light speed is to be constant? Or does it just mean the one-way light speed is variable and the two-way light speed is constant? So when you sort of like do an experiment such as the lunar ranging, if you agree that it's showing the one-way light speed as being variable, does that contradict what Einstein's relativity is saying when you now reinterpret it as it's allowing one-way light speed to be variable? It's just the two-way light speed that's going to be constant.
Yeah, I understand.
So this is all moving the goalpost upon what Einstein's relativity is.
Yeah, it is moving the goalpost.
When you do an experiment, you want to have a theory to test, which is going to be precise and clearly defined as what it's talking about. But in the case of Einstein's relativity, the theory is vague and it gets reinterpreted. So if you do an experiment to show one-way light speed is not constant, does that disprove Einstein or not? And the answer is we don't know, because Einstein's relativity is not a precisely defined theory.
Yeah, it's not. That's right, it's not. But,
so that is the problem. It fails the scientific method. Einstein's relativity fails the method of science when you've got a theory that can be reinterpreted.
Yeah, it's a mess, as you said.
Yeah, it's a mess because you've got a theory. People say it's right, but people are interpreting the theory in different ways.
Yeah.
So when you go back to say, well, Rommel and Bradley, well, that was being interpreted from Newtonian physics at the time, and then it's supposed to be now interpreted by Einstein's relativity. But Einstein's relativity is vague as to what it really means. That is the mess we're in.
Yes.
Okay, so thank you, Dennis. Is that it?
Yes, thank you.
Thank you, Dennis.
I think James Hugh.
Okay, Franklin. Okay.
He's bringing up a question here about.
Okay, Franklin. What did you make of any of it?
The lunar ranging actually works. I'm going to bring up James here. let him ask his question.
Hello. Oh, James.
Hi, Roger and Franklin.
Things
Franklin, you're a very
seem to be a
patient
bit slow
man.
at the moment.
Roger,
Hi, James.
this you don't explain how the lunar laser ranging data disproves relativity. You merely cite some papers of people claiming such.
Yeah.
That's far below the standard for these presentations, in my opinion.
Well, I would have read through the papers, but it looks too small on my screen, so I couldn't.
Well, just tell us, how did they disprove it? I'd like to know. That's supposedly the topic today, right? Just tell us in your own words what they did and how they disproved it.
Well, I dispute what they're saying. From my way of looking at things, I want them to precisely define what special relativity is. And you need to do that to disprove special relativity. And so these papers, they don't precisely define what special relativity is. They seem to be assuming that the one-way speed of light, when it is variable, disproves relativity. When I have this interpretation problem with special relativity, should special relativity be interpreted that way? And then when you get to the particular details of the actual experiment, then the critics of these papers then start criticizing the experiment and disagreeing with how the experiment was done.
Okay, well, so in other words, you're rejecting these papers.
No, I'm not rejecting the papers. I'm just saying that it is an interpretation problem. You need to know what special relativity is before you can disprove it. And if you're going by what Einstein is saying in all his papers from 1905 onwards, it's difficult to understand what the theory is really supposed to be. So what sort of prediction is it supposed to be making about lunar ranging? It's not clear. It doesn't make sense. And then if you want to go to people who've sort of like supposedly clarified things, like Pauly in his book, The Theory of Relativity, well, Einstein started disagreeing with that. So you've got a divergence of how you are supposed to understand what relativity is. And that's why the theory fails. You haven't got a properly defined theory. So if you haven't got a properly defined theory...
Why are these lunar laser ranging papers even included in today's presentation? We don't know what they're saying or exactly what their analysis was.
Right, I can put the links up to them.
And why? How are they relevant to today's talk? This is a complete hole.
It's relevant that there are papers that are saying that special relativity is wrong. They're saying they've done experiments and they've shown that special relativity is wrong. So that's relevant in that context.
But we're not going to say what the experiments were and what their findings were.
Well, it's about measuring.
Come on,
it's about measuring.
This is like a non-event.
It's about measuring light speed from the moon to the Earth, and so you can go into details about how
were they measuring light speed from the moon to the Earth.
Well, that's what the critics would go. That's what the critics of it would go into. They would sort of like criticize the way the experiment was done, and they would dispute the conclusions that those papers were coming to.
No,
my dispute on it all is we can't even tell what special relativity.
Normally, lunar laser ranging refers to measuring the distance between Earth and Moon.
Yeah.
It doesn't have anything to do with measuring light speed. Nothing.
Well, you're taking into account the distance. You're measuring the distance, and you're also getting the time of how that distance is covered by light. So what they're saying is the speed of the light is not constant for that.
Yeah, one of the papers you presented, clearly said that the speed of light was found to exceed the canonical value. So somehow they were making a one-way light speed, or either that a two-way that was showing that it was coming back faster than the canonical speed.
Yeah.
Although I'm not sure.
That would just mean that the moon is closer to Earth.
That could be. I mean, I would imagine that we could make, by optical means, make a determination of how far any point on Earth is to the moon, I suppose. I'm not 100% sure we could do that. But presuming that, we could make a precise presumption of distance, then we could send a light beam and it would have to come back, and we would have no information until it did come back. And then we could determine the speed of light, at least the two-way speed of light. And then I suppose we could determine it was not the same as the canonical value. Although I don't know whether that tests the invariance of
lunar laser ranging, the actual name of the procedure, is a measurement of distance, not of light speed.
Yes, but
and it's assuming that at distance A and distance B, those distances between Earth and Moon, two different distances, that whatever the light speed is, it's not a factor or a significant factor in measuring the difference in distance. This is the whole idea of lunar laser ranging. So I find it rather surprising that somehow people are saying, oh, we know the distance between Earth and Moon, and we can use the data to then measure light speed. I mean, this, as far as I can see, is pretty much complete nonsense.
Yeah, it seems kind of circular, don't it?
Yeah. So, like, even, carpenters and surveyors use these little things that bounce light off of a mirror to measure distance. This is what laser ranging means, okay? And somehow, all of a sudden, we're citing papers here in supposedly a technical session of here, and we can't say what it is that we're saying except that the people are wrong. I find that most unsatisfying. I'm sorry to be a critic in this way, but it seems like we don't even have a good idea of what lunar laser ranging is as a procedure. A number of different observatories around the world use this technology to measure the distance between Earth and Moon. Now, I don't know of any way, or at least in today's presentation, there's no explanation of how this data can be used to measure light speed. None whatsoever. And so, again, what is actually the reason for including lunar laser ranging in the title of today's talk? We're just left with the idea that Roger says there are some papers and they're garbage. Well,
I'm not saying the papers are garbage, and this was not a technical session. This is a session dealing with the theoretical issue of how do you interpret Einstein's relativity, and you need to be able to do that before you even start doing experiments. I was just pointing out that
I'm not getting how lunar laser ranging is the papers that you cite are contributing at all to disproving relativity. If that's your thesis,
that is not a thesis. I'm pointing out that there are these papers which are saying that special relativity is wrong, and I didn't go into the technical details. This is not a technical session. We could do another session on the technical details, but the problem that we should be starting with is we haven't got a precisely defined theory for Einstein's relativity. So even before we do an experiment, we need to know what Einstein's relativity is. And if we can agree what Einstein's relativity is, then we can do an experiment, and then we can go into the technical details of that experiment. But at the moment, the theory of relativity is not a precisely defined theory. And that was the culmination of what I've been showing in the previous talks. I've shown that Einstein's relativity is ambiguous. In one talk, I pointed out a person who was saying the Sanak experiment disproves Einstein's relativity. But then when you get into the details of that, still Einstein's relativity is not a precisely defined theory. And what we were just going by was what he thought Einstein's relativity was. And you've still got that same problem with these papers, which are saying that Einstein's relativity is wrong from the lunar ranging experiments. And that is the issue I have been dealing with, that Einstein's relativity is ambiguous. And before you can even disprove it by experiment, you need to say what the theory is.
Well, like the papers that you're here, we have on the screen now a review of lunar laser ranging, a review.
Yep.
Well, if we're talking about experiments, there's a hypothesis, there's an independent variable, a dependent variable, one or more, and some measurements and a conclusion as to whether or not the hypothesis, forget all the different interpretations of Einstein's work. Those papers, if they are in fact experimental in nature, do have a hypothesis which pins down a specific thought or premise, and an experimental design of independent variable measurement and dependent variable measurement showing some sort of cause and effect relationship. That's what experiment is about in science, which would be of interest.
Yeah.
That's all I have. I'm sorry to be, a bit negative. I like to be upbeat and positive, but simply to say there's confusion in the theory, and so therefore these papers on lunar laser ranging are not even worth looking at, because other people have confusion about what is or is not the proper hypothesis. Why not present to us in the lunar laser ranging what their hypothesis was? That's not all that technical. What their operational definition was for the independent and dependent variables that are involved in any experimental study, and what the statistical significance of the results was, and what how that bears upon the hypothesis to accept or reject it. That's what experiments are. And it seems like we've sort of left the domain of science, and we're just saying, because different people have different hypotheses, there's really nothing we can say about any thing, Sanak experiment or any of the others, because all different people have different hypotheses.
Yeah. So am I back again? Can you hear me?
Yeah. I'll sign off. I've had my little say.
Thank you. Cheers. Thank you. So, hi, Franklin. Am I back? Hello.
Yes, you're back.
Okay. Yeah. So the problem is, I've pointed out, he's talking about we've left the domain of science and all, and we need to know what the hypothesis is. But if you're reading Einstein and other people who are talking about relativity, they've all got different ideas what relativity is. And if you want to go into the experiments for those papers, they've got their opinions about what Einstein's relativity is. And so how are we to decide whether what those papers are saying have the correct interpretation of Einstein's relativity when there's so many different interpretations out there?
Yeah, I see Jim. I just put up one of Jim's comments here.
Yeah.
And he was trying to explain what the lunar ranging experiment is. But let's put up Jim here and see whether he can explain what he meant by that.
Hi. Yeah, he took he looked at measurements that other people made of the time of flight for sending a pulse to the reflector and back.
No sound. I've got the sound. No sound.
Sorry?
Can anybody hear me? I've got no
yeah,
sound.
we can hear you.
Yeah, Jim's got no sound.
No, I can hear Jim.
Can you?
Yeah, go ahead, Jim.
Yeah, and he showed that as the Earth rotated. Okay.
Yeah, I got you. Thanks. Okay.
And he showed us as if as the Earth rotated and the pulse telescope that was sending the pulses moved to separate distances from the moon, that the time to reflect changed in a way that was consistent with an ether theory, essentially, and not special relativity. The part of the problem was that he had to make some, or he made assumptions about a universal reference frame instead of a local ether type reference frame. I think if he had done that, he would have had a stronger argument. But he was roundly criticized by relativists as any dissident type explanation would normally be mentioned. And he did, in trying to define a reference frame for the experiment, make some kind of weird ideas, because he was trying to do it with what I consider a wrong starting assumption.
Yeah, I noticed that, one of the papers that Roger had shared, I think mentions this point that, they talk about the light clock. And, I think Harry was criticizing me about talking about how the light clock works. But one of the presumptions is that the light beam would move along with the clock like a physical ball. But instead, what this laser lunar ranging thing is showing is that if you do try to build a clock out of a light, and when you shine the light up to the top of the ceiling as the train moves, the light beam does not move with the train. It would actually hit a point above the train, and it would not actually reflect back. So that is what this is saying. It says what happens to a laser beam that points from the bottom of a train at rest to a point in the ceiling when the train is moving very fast. Will the beam still hit this point, or will it hit the ceiling behind that point? In the years around 1900, scientists were convinced that the photons get a lateral momentum in the direction of movement because they are particles. But our fine mind concluded that the mirror emits photons and is therefore a light source, and together with Finneg's second SDR postulate, and hence laser beams should hit the ceiling behind this point. This can be tested with the return rates of photons from a mirror on the moon. The results show clearly with an error of probability that photons do not get lateral momentum but arrive at that location when the Earth was 2.2 seconds before. And so besides the detection of an additional velocity of Earth in the universe, this article proves that Einstein's geometric space-time idea is wrong because the physical basis for that is wrong. So that just proves that light clocks would never work, and that we do observe that.
Hi, sorry. Can I come in? Yeah, I was thinking of doing a discussion on the light clock because I've got videos on that, and we can start of come to show the dispute which goes on with the light clock, where people interpret it in different ways. It is another confusing area of trying to understand what's going on, and people put different interpretations upon it.
Yeah, although this really doesn't have to do with the light clock. It has to do with the fact that light travels differently through space. It just, if you put a mirror on the moon, it's not going to come straight back to where you pointed it. So, because the Earth is going to move out of the way, right? So you can detect an absolute motion of the Earth.
Yeah, you're supposed to take into account the movements going on like that. So whether they're doing it properly, you can start disputing they've done the experiment properly. But sort of like if you get something simple like a light clock with the lights bouncing up and down between the mirrors, people raise objections to that as well. It's another area of great confusion as to what Einstein's relativity is saying about that.
Yeah, although my confusion is, about to say the video. So the video says that, and Veritasium says that, it's impossible to do anything other than measure, say, the two-way speed of light. And so
some people take that interpretation that you can only measure two-way light speed.
Then how could the lunar ranging experiment, which is of course a two-way light experiment, really say anything?
So that is part of the criticism, because of all the variety of different interpretations of Einstein's relativity. Some people take the point of view you can only measure the two-way light speed, and so if they look at that paper, those papers saying that the light speed is variable, they'll start criticizing it, saying it's wrong. You couldn't do that actual experiment. So that's another technical issue of the comeback on the criticisms. But some people do have the belief that the one-way light speed is constant from Einstein's relativity, and so they would dispute it from a different direction.
Well, the one thing I don't understand, I mean, this is a relatively modern video done in the time of GPS. So why do not any of these videos mention that GPS, as far as simultaneity goes, they set up a series of satellites which have to be synchronized.
Yeah.
And in order for this to work. And I
think from our expert, the GPS engineer was Ron Hatch, who's now sadly passed away. He could have gone into those issues where you're using just one frame. You're treating one frame as what you want your clock synchronized to. And I think it's the easier frame.
At least the video helped clarify, because when I read the 1905 paper, that was my exact question. Is like, what on earth is Einstein assuming? He's assuming that the light signal from clock A to clock B is going to be the same as from clock B to clock A, and I'm just screaming in my mind.
He doesn't. I don't think he tells you that. He does. The light signal, he's not telling you is the way light speed constant or not. From A to B, that's light in one direction. Then B back to A, that's light in the other direction. And he's not telling you what the speed is for that. He's telling you what the speed is for A to B and from B back to A.
I'm quite convinced, based on the video, that Einstein was talking about the two-way speed of light and not the one-way speed of light. But he
doesn't mention two-way light speed, and he doesn't mention one-way light speed. So unfortunately, it's now an interpretation being imposed upon what he's saying.
Well, no, there's no.
He didn't clarify it.
We see the equation, and that is the two-way interpretation. There can be no other interpretation than that. I mean, 2AB divided by the time difference. That's the two-way speed of light, right?
Well, that's what we interpret it as now.
Is that, like I said, I don't know why they don't mention GPS, because GPS, the clocks have to be actually synchronized. So they're saying that no clocks can be synchronized, but yet indeed that's what happens. And in GPS, you have two satellites, and what you're doing is that you're actually sending the time that's on the clock in the signal. right? This is how the GPS works. Like I'm in the middle, 1 o'clock, they both transmit exactly at say 7 a.m. And then when they reach my head, my receiver can detect the time and what the difference in time when I receive the 7 o'clock signal. And by doing that, I can determine where I am on the Earth. You see, so it would seem to me, and that's how they synchronize these GPS satellites, I believe, because if they didn't get this right, then I should be able to tell the one-way speed of light. Because if the speed was different, like I have a transmitter here and I have a transmitter here. And if they're transmitting in a uneven manner, like it's slower this way than it is this way, then all I have to do, I would think, is to stick a receiver in the middle, like my head. And then when I think my clocks are synchronized by whatever mean, when they transmit, then if the two-way speed of light is the same, then they should both reach my head at the same time. But if they are not, then one of them will reach my head before the other one will. And then I will know that epsilon is not 1/2. I would think. I mean, that's just my thought. After watching the video, I just came up with that. But it would seem that would be a way of doing it.
I've been to Oxford University where they do talks on relativity, and it's some years ago now, but there was an expert on relativity who was looking at GPS, and so he gave his talk. And what he was doing, he was looking at the data from GPS, and from this analysis of the data is saying it agreed with Einstein's relativity. So that's where they get the proof from for that. They're saying, Einstein's relativity is proven because GPS agrees with it. But you then got the problem of, well, that expert, how does he interpret Einstein's relativity? Does he interpret Einstein's relativity with all this stuff about two-way and one-way light speeds and universal reference frames and all that sort of thing? How is he interpreting Einstein's relativity? And that's a detail that they don't go into.
Yeah, because the thing is that the only equation you can really look at for these effects is like the Lorentz equation, the whole Pythagoras theorem thing.
Yeah.
But they don't mention that requires the presumption.
I've talked to lots of people about relativity, and hopefully from your point of view, Lorentz theory is different to special relativity. Is that from your point of view?
Well, I don't know. Well, we have our expert here. We have Nick. So maybe we'll bring up Nick. Maybe Nick can clear that up for us. And you're muted, Nick.
Hi.
Need to unmute yourself there, Nick.
See if I have my...
There you go. We can hear you now.
Excellent. I thought that was a wonderful video that at the start of the program.
Yeah.
He makes an excellent and logical point. And there were similar criticisms of Einstein. I think a lot of people think that Einstein was accepted from the start, and no one's criticized him. At least when I was at Harvard, they never mentioned a word about criticism of special relativity. And not only Reichenbach, but Jammer independently came up with the same idea that you could pick any fraction other than 1/2, and you would get a theory that was indistinguishable from special relativity. So arbitrarily choosing a specific fraction for epsilon, really the problem is it guts all of the physics of what happens. For instance, in the twin paradox, special relativity cannot tell you what's happening, what's the rate of time difference accumulating during the outward and inbound trips. Allegedly because, as the relativists tell me, all observers have equally valid views, all inertial observers, and each one of them disagrees with the rate of the proper time difference accumulation at various points. So that was a strong argument against the validity of special relativity. And Franco Solari, who won the highest prize for an Italian in Italy for an Italian physicist, agreed with them and wrote a whole series of papers about that as a major weakness of special relativity that needed to be addressed. We talk about Einstein changing his mind. I don't criticize him for that. I think he was a very good critical thinker. The only problem was that academia didn't follow his critical thinking mode and was open to new ideas. They just say the special relativity is correct while changing the meaning of it. The relativists who in their conversation and arguments present two totally different views within the same argument. So I'm not sure Roger's goal of finding out what does relativity really mean is achievable. For one thing, as he correctly points out, Einstein kept changing his mind. Just one more side thing, and then I'll talk about GPS and two-way view of speed of light. The standard for the meter was changed a couple of decades ago so that if you use the standard for the second and you use the standard for the meter, which is in terms of distance traveled by light in a second, as defined by the new standard for the second, then you have to measure the speed of light as c, whether it physically is c, into the time point. I would disagree a bit with Franklin about the 1905 paper, because 1905 paper, all the logic depends on the one-way speed of light being c. And Einstein's synchronization, while it's expressed in terms of being one half the two-way, is rather explicit that, hey, all the logic that follows is based upon the speed of light being equal from A to from B to A. So it's the one-way speed of light being c it's a fundamental axiom, really, of special relativity. And relativists always tell me that, hey, if you're going to do experiments, then you have to be sure that your clocks are synchronized by Einsteinian synchronization. So that's an indisputable point on that 1905 paper and how relativity is taught in most schools, at least as of 1960.
Yeah.
But Ron Hatch, who I talked with for a long, long time, over many, many years, consistently said that in GPS, the speed of light of a signal going from the satellite to the receiver on Earth depends on the movement of the receiver. In other words, the speed of the receiver, the motion, the velocity of the receiver. So that's, and Ron had 30 patents in GPS, and he knew the data of GPS as well as anyone, whether he was alive. But he mentioned that, politically, GPS management has to say that GPS is built on special relativity, even though Ron, was rather explicit that it disproves special relativity.
Yeah.
So that's basically the two big points: GPS relativity. And
okay, can I respond to that then? Thank you, Nick. That finished, is he?
Well,
thank you, Roger.
Okay, thank you. So going through that, can I go through
the
them?
fact that GPS establishes an absolute simultaneous preferred frame itself disproves special relativity?
No.
That's even possible?
No, because that sort of echoes what Solari did. He first, because of Jammer and Reichenbach, he said the key thing is we have to have absolute simultaneity. But the problem with Solari's solution was he said, okay, we arbitrarily choose a frame to be the preferred frame. So while you had absolute simultaneity for everybody, it wasn't necessarily true physical simultaneity. But GPS data suggests that at least within the vicinity of the Earth, you can have a physically accurate description of simultaneity that's agreed to by all. And I'm not saying that GPS has that, but it comes very close. So you could have simultaneity, quote unquote, defined simultaneity, but not really have true physics. But GPS does a really good job to extremely high precision of having absolute simultaneity that's in sync with what's happening physically.
Yeah, during the video, that they were harping on the fact that they were saying that we reduced the problem down to an actual physical thing, and that, I don't think they actually said it, but that there is one preferred frame where epsilon really is 1/2, and that everyone needs to agree that that's the one we've seen.
Yes, that's true. And that's Lorentzian theory, which is on the opposite end of the spectrum of special relativity. The equations look the same, but because in Lorentz theory, velocity is absolute velocity to the single preferred frame, which in his mind was the ether, and in special relativity, it's different. For the single preferred frame is different for every single inertial observer, and they come up with different physics for what's happening, except for those things that are Lorentz invariant. And that's the one place where special relativity will agree with Lorentz's original ether-based theory. So I'm not necessarily an etherist, but the data from GPS is absolutely crystal clear that there is a single preferred frame, particularly for viewing space and time.
Okay, thank you. Thank you. So I'll go through the points. To go back to the earlier one, the twin paradox. I think I was wondering if to do a session on that, because I think I found two relativity people, pro-relativity people, and they're disagreeing about the twin paradox. So that would have been an interesting session. So people who believe in relativity, they do disagree upon what the twin paradox means. And on the issue of Einstein changes his mind, I don't think it's very good. You pointed out, yeah, it's good that he's a critical thinker, but he's changing his mind. And if you're trying to come to the reasons why he's changed his mind, he's not really giving you enough information about that. And so as to the other issues about light speed, well, if it's defined as light speed in the case of making the standard for meter and second, and the other issues about Einstein synchronization, if you're defining the light speed as a constant, the problem there is, well, physics is supposed to be about finding out things by observation and measurement. And so you are taking relativity away from being something that can be experimentally tested if you're making it a definition. And then finally, upon the preferred frame, which you bring out with the GPS, I think I've got a Nobel Prize winning physicist who's saying that there is a preferred frame, and the people in the physics community who think there's not a preferred frame have got it wrong, and Einstein's relativity has the preferred frame. So once again, you've got a problem in interpretation of Einstein's relativity. And so that's always going to be the problem. People are having different interpretations of Einstein's relativity. Thank you. Can you come back now, please, Franklin? So I made my point.
A question from Andrew here.
Yeah, Andrew. Right, okay.
Apparently has never heard or used of an ECI, and what's the point of it?
This is what Ron Hatch was dealing with for. He's a GPS engineer, and sort of like you're using. I think ECI stands for Earth-centered inertial frame or something. I think so. He's using just a preferred frame for his synchronizing his GPS. Yeah, that's not really the topic for this talk.
Well, I think it is relevant in that the lunar, any kind of lunar ranging or two-way transmission of signals does have relevance for the ECI. Now, the ECI, if you were to imagine that the Earth is in fact the center of the universe, and the Earth was spinning around a point in the center of the universe, so if you get that picture, you made a graph paper and you graphed everything out, and everything was fixed. And then if you use that as the preferred frame of reference, then it turns out that all the calculations that GPS uses in order to precisely locate me on the Earth with satellites thousands of feet, that works. And that's actually the only frame in which this would actually work. So that is the definition of the Earth-centered inertial frame. I mean, it doesn't even take any account, say, the motion of the Earth around the sun.
So ECI does stand for that, is it? It does stand.
But people try and confuse that, but it's like, no, it's as if the Earth was the, in fact, geometric center of the universe, and there's a point that's fixed in the middle of the Earth that the Earth is rotating around. The rotation is not part of that. I mean, some people want to think that the whole Earth frame rotates, but it doesn't. And then you just apply Lorentz theory, right? Assuming that is the frame you're talking about. GPS applies just straight Lorentz theory, and that turns out to work, right? So the point of it is that frame works. Any other frame, if you try to do just like relativity, where every single clock and every single satellite is as right as any of the others, it just won't work, right? The only way to make it work is to get all these clocks actually synchronized, so that when it says 12 midnight, they all say 12 midnight at precisely the exact same moment. And when you transmit a signal from a satellite to some place on Earth, it has to take into consideration that you're rotating on the Earth, and you may be either approaching or retreating from that satellite, depending on which side of the Earth you happen to be on relative to that satellite. So, and all of these things have to be taken into account to get GPS to work.
Yeah. So there's more technical stuff which is avoiding.
So we do have, I'm monitoring the questions here. So if you guys have some direct questions or direct comments, we'd like to hear those. So like we have another comment from Jim saying that the ECI influence for radiation only extends to 1 million kilometers. where the sun's reference frame takes over. Oh, well, that's an interesting point, because I don't know whether I've ever heard that point from Jim. So, Jim, maybe you can clarify where this precise value comes from. And you're muted, so you have to unmute. Yeah, you're still muted there, Jim.
Yeah.
No, well, we also have another question from Andrew here. Is that if you use ECI for GPS, how would you transform that measurement to find the location of the IIS or a different satellite? Now, I would think that the problem of that measurement would work anywhere actually in space, because all you're doing is that you're presuming that you see several satellites, and you're just measuring when the time signal gets to you. And by using that difference, you can triangulate your position relative to those satellites, right? I think that's just a GPS question, right? So yeah, I don't think you'd have to transform anything. I think you could probably take your terrestrial GPS receiver up to the IIS, and it'd tell you, yes, you are this far up in space. Is probably what it would do. I'm only guessing, but
okay.
But what do you think, Roger? If I take my terrestrial GPS,
is Jim coming back? So, oh, is he
well, I think he's unmuted now, so let's see whether we can get him back. Okay,
yeah, I found the mute button. I'm sorry.
There you go. So tell us about, is there a limit to the ECI of influence?
Well, yeah, as I've been
still no saying.
Sorry?
I'm not getting any saying.
Can you hear? Because I can hear Jim. I'm not sure if Roger, you maybe have an audio problem. But go ahead, Jim.
Yeah. Yeah, I've been trying to advocate for what's called the local ether model.
Still no saying.
Better?
Now go ahead, Jim. I think Roger's having a problem.
It essentially says that the preferred reference frame, or ether essentially, is a local phenomenon based on the or that corresponds to the Earth's or to the local gravitational potential. So near the Earth's gravitational potential dominates, but as you get farther away, it becomes weaker until it matches up with the sun's gravitational potential, and that's true of any celestial body, like a planet. So it has its own local ether halo surrounding it. So it's like a halo surrounding the Earth in terms of acting as a preferred reference frame. But it follows from the idea that it's corresponds to the gravitational potential surrounding any celestial body, and it's a hierarchy. So the sun has its own inertial reference frame, essentially, for interplanetary electromagnetic propagation, and then as you get farther away from the sun, the intragalactic, the inertial reference frame of the or local ether halo of the galaxy takes over, and then you go farther out. You have galactic clusters, and who knows where it ends. But
yeah, okay.
It's a hierarchy.
Yeah, hierarchy. Okay. Thanks.
So Jim, so your statement was just kind of based on the gravitational influence. So we don't know that for sure. I know
Well,
that
it happens to match up with electromagnetic propagation is what I'm trying to say.
because I know you've been trying to advocate, we should send out a special purpose satellite to go out into space and try and find the limits of say Earth's influence, or send the MMX experiment out into space and show that at some point you can measure the speed of the spacecraft out in, say, outside the influence of Earth's.
Absolutely. Absolutely.
Because we don't know.
But in the meantime, you want to do it in low Earth orbit because it's cheaper. It's not as good because you've only got the satellite's velocity, orbital velocity. But obviously, once you get out into interplanetary space, the orbital speed of the spacecraft is the 30,000 kilometers per second, the same that was looked for by all MMXs so far.
Well, as an experiment, I would like to see them try and set up GPS around, say, the moon. And now it would be curious to see what frame of reference works for the moon. And it would be quite surprising to find out that the Earth-centered inertial reference frame still has to be used for the moon, for example, right?
Yeah, that would be a good test too. I agree.
Yeah, so I would, if I were like a
what's cheaper? What's something that they won't do it, NASA won't do it, even around the Earth or on the ISS. So you would have to privately fund it.
But I think probably all of these satellites that they're sending around the moon probably already contain precision atomic clocks, and it would just be a manner of appropriating their data to find out whether it's true or not. Maybe, I don't know, but that's just kind of an example of if you took the ECI frame thing to the extreme, that even if you tried to set up a GPS around the moon, you'd have to find out you still have to use the frame of the Earth in order to correctly calculate the velocities. Because I think there was a question by Andrew about, if you have to transform the frames, then what's the point of that whole thing? The thing is that with the ECI, that sets the absolute velocity for everything in the system. You can, with 100% accuracy, say what is the velocity and direction of a particular satellite. So it's not not that there's any kind of frame transformation, because you don't have to transform the frame, because the ECI is the one frame. And then, yes, you have to use triangulation, because I think its question indicated that if you don't have to use triangulation, but no, you have to. That's how GPS works. It works through triangulation. And the trick is making it so that precisely where all your triangulation points are coming from, right?
Yeah, and the time differences are so small in a picosecond that you probably would have to look for it carefully to find it.
Well, it's a wonder how GPS works, because it is relying on these picosecond differences. Literally, when the GPS clock transmits 7 a.m., it gets to my GPS receiver in my phone at slightly different times. So, and based on that, it calculates how far away the satellite is from me in like 2 or 3 different places, and based on that, triangulates my location on the Earth, which I think is, and it can do so with an accuracy of about 50 feet, which is, I find hard to believe that actually works, but that's how it works. Yeah, this is the question that Andrew was asking here. So why use any frame transformation if you don't need it to triangulate location? It's like, yeah, we're not using any frame transformation. We're just establishing one frame as the frame, and we absolutely need it to triangulate location. So, but like I said, if you have any other follow-up questions, I am monitoring the chat.
Yeah, by the way, you also have to take into account the Sagnac effect, as you were saying, that the time to transmit or the time to receive is also affected by your motion of your receiver while the pulse or information is being sent from a GPS satellite.
So we have Andrew's question here, but I think maybe Nick is more qualified to answer this one. But we have satellites orbiting the moon and sun and can still use special relativity and GPS to locate them. So is that really true? And I think you're muted there, Nick. Nick, you're muted. Need to unmute yourself there, Nick.
There we go. As I wrote in the chat, I said Franklin is correct about the ECI, but note that the ECI frame can only be used as the preferred frame in the vicinity of the Earth. Between planets, one must use the solar system barycentric frame as the preferred frame. So on the Earth, we use the ECI frame. When NASA tries to track things in interplanetary space far from the sun, it uses the solar barycentric frame as the single preferred frame. And Hatch had some discussions with the NASA scientists who thought they were using special relativity because Lorenz's equations for clock dilation and whatever are exactly the same.
Been like it for a long time now.
Are exactly the same, but
so
they have to use
muted.
No. So NASA, and he pointed out, NASA, you're not using special relativity, you're using single preferred frame, but he didn't get anywhere with them because they weren't even aware of Lorentzian theory and preferred frame theory. So the preferred frame tends to be the local frame, and it appears to be like the local gravitational rest frame, which around the Earth, interestingly enough, is a non-rotating frame.
I'm not hearing anything. Threatening, you hearing it?
Yes, I'm hearing. I'm not sure. See, Roger can't hear you for some reason. But
Roger, I think his things are delayed or something. So what was I saying about? Oh yes, and I don't know if the gravitational rest frame is non-rotational because it refreshes itself so fast that any rotational motion gets lost in that refresh.
He's saying now. He's just come through. Oh, he's gone again.
Okay, so that was my answer to Andrew.
He had a quick burst of sound from my end, and now it's gone.
Yeah, I'm not sure. I think, Roger, you just may be having some connection problems since we weren't able to share your screen, but the rest of us can hear. So
it's weird. It's playing up weird today for me.
Yeah, it's playing up weird. But, just to add my own commentary on this particular question, which is, I think that when people talk about things like special relativity being confirmed, they're really talking about Lorentz theory being confirmed, because mathematically, special relativity and Lorentz theory, the mathematics are exactly the same. Mm-hmm. And so you can, all of the experiments they can point to say, mm-hmm. Yeah, we've got the time dilation and that stuff going on.
Mm-hmm.
But once again, the only real difference is that Lorentz theory has a preferred frame and special relativity does not. And the thing is that if we were to use GPS, assuming special relativity's assumption of no preferred frame, a GPS flat out wouldn't work. It just
when I've talked to people about relativity, some people seem to think that Lorentz theory is special relativity.
Mathematically,
when you go to what Einstein's saying, it is supposed to be a different theory in the 1905 paper anyway. So people who have this interpretation problem of there's two different theories, what Einstein's saying in 1905 and what Lorentz is saying, I think, in 1904, and people are thinking the theory is what Lorentz is saying, but they don't understand it's Lorentz saying what they believe instead of Einstein. They're still attributing Einstein as being the one saying it. And so it's this awful confusion still going on out there.
Yeah, so Andrew has a follow-up. How would I use the local ether model in nuclear physics? And, I would say that you just use it the same way that you've used special relativity. You're assuming in nuclear physics you have the laboratory frame, and we're presuming that in the, say, local ether model, that is what your laboratory is fixed to. So you can go ahead and, use what you thought was special relativity, but really you're using Lorentz preferred frame theory.
Yeah, using the laboratory lab frame for when you're doing nuclear physics. And so if you're getting confused between what Lorentz is saying and what Einstein's saying, you're not really understanding that there is a difference going on. And you're just doing the maths and you're saying, oh, that's Einstein's relativity, when really it's more sort of like what Lorentz was saying.
Now, I was really interested in what Nick just said there, which is, to answer that question, if you
didn't get any of Nick's, I couldn't hear any of it.
Well, he was saying that NASA, when you're trying to, orbit a probe around Saturn, or try to get a probe out to Saturn. I don't know what happens when you get to Saturn, but when you're trying to do precise distance ranging, then you have to use the sun baryocenter frame of reference in order to make those things work. Right. So that's more along with what Jim was saying, that he was saying that the gravitational sphere of influence perhaps makes a bigger impact on what's going on. But we are towards the end of our time here. So I'm going to have you just summarize, and we'll close out the session. So why don't you go ahead?
Right. Okay. Thank you. Yeah. So the summary is that you have in these papers out there, such as the lunar ranging experiment, dealing with that, and they're saying that its relativity is disproven, but you can start disputing interpretation issues with relativity, and it's very confusing as to all the different ways that people have their opinions upon what special relativity and so forth is. And so there's a kind of confusion there about what's going on. So when these papers are saying, oh yeah, light speed is variable from the experiment, well, you can dispute that on technical issues and saying, no, they've done the experiment wrong. Or you can, if you are accepting that the experiment is done properly and the speed in special relativity as allowing upon the reinterpretation of what Einstein was saying in 1905 when he was saying light speed is constant. When he was talking about that, did he really mean two-way light speed, or did he mean one-way light speed, or did he mean both one-way light speed and two-way light speed were constant? So you've got this awful confusion of what is supposed to be Einstein's relativity. And if you look for Einstein to try to clarify things, well, he's changed his mind a lot. And if you look for other people who were working on relativity, well, Einstein wasn't necessarily agreeing with what they were saying. So that is the mess we're in. Thank you. And for other talks, I could go into the technical issues of the lunar ranging experiment or I could go on to other things like the light clock, or I could go on to about the twin paradox, and showing that the confusion just carries on to those other issues as well. Thank you. That's the end of this little session. Thank you, Franklin.